Hello. How does gravity work to provide circular orbits or nearly circular orbits? How does gravity lead to Kepler's laws? Well, in this video, I'm going to try to answer those questions. So let's begin by looking at a quick little sketch of the Earth orbiting the Sun. As you can see in this diagram here, the Earth is going around the Sun in an approximately circular orbit. And as we know from other things in class, if this type of thing is happening, then we know that the acceleration must be toward the center. This is called a centripetal acceleration. We know that because if the Earth was left to its own devices, it would just go straight. But it ends up going something like this. It makes a turn. How does it make a turn? It must have some force that's acting on it like that. And likewise, if it were traveling just tangentially like this, and sometime later it ended up going like that, there must have been a change that caused it to do that. And if I can draw that here, imagine tangentially going there and also in that direction, there must have been something to cause it to change its course. And likewise here again. All of these large arrows are basically pointing toward the center. And this indicates that there must be some sort of force or acceleration that's pointing things toward the center to cause it to continue in this circular orbit. Well, what is that force? Newton thought that it would be given by something like this. The force of gravity is given by capital G, and in our diagram, we've got the mass of the Sun as the central one, and then the mass of the Earth. And then it's divided by the distance between these two things squared. And this would be the distance between the center of the Sun and the center of the Earth. Okay, so that's R. R is right like that. So here's the Sun, and here's the Earth. So this force will cause the Earth to be attracted to the Sun, and likewise the Sun to be attracted to the Earth. Notice that these two arrows will be exactly the same magnitude. And this is in accordance with Newton's third law, which says that for every action, there's an equal and opposite reaction. So this type of attraction here must be equal to that type of attraction there. So this then is the force that is causing the Earth to be accelerated centrally toward the Sun. And every time we have circular motion, we've got this centripetal acceleration. So if I want to write Newton's law, his second law, F equals ma, for this type of system where I've got a circular path going around the Sun, then I would say the force that I know is going to draw the Earth in toward the Sun is just given by this G, mass of Sun, mass of Earth, divided by r squared. That is this force here. And now I make that equal to the object that's being accelerated centrally, and that's the Earth here. And so that's the mass of the Earth. And now the acceleration is a radial acceleration or a centripetal acceleration toward the center. So this is our equation. I'm going to elaborate it a little bit and simplify it. So G, capital G is a constant. I'll mention that in a second. Mass of the Earth divided by radius squared equals mass of the Earth. And as we talked about in class, the centripetal acceleration is a special type of acceleration. It's given by v squared over r. Make sure that's a square over r like this. So this equation is certainly fine as it is, but I can simplify it a little bit. The mass of the Earth ends up on both sides, so I cancel that. And then I get g, mass of the Sun, divided by r squared, equals v squared over r. Now, a typical way to simplify this equation is to divide or multiply both sides by r. So if I multiply this by an r and this by an r, these r's will cancel, and this r will drop one of those powers. So then I get g times the mass of the Sun divided by r equals v squared, and I can take the square root of both sides. G, mass of Sun, divided by r equals v. This equation is where I wanted to get to. So this is one of the first things that Newton's law of gravitation tells us if we've got a circular orbit. There's a relationship here between the radius of the orbit and v, the velocity of the orbit. And what it basically says is this. If the radius gets smaller, then this term over here is going to get smaller. Well, actually, sorry, just the opposite. It's going to get bigger. So this term is going to get larger. So if the radius gets small because it's in the denominator, then this term will get bigger, and that means that the velocity will go up. And so if you've ever seen these coin funnels where people in a store, they often ask you, oh, put your coin in and have it orbit around like this. It goes around and around and eventually kind of goes smaller and smaller into the funnel. What you notice is that it goes much faster as it's in the shorter, smaller part of the funnel at the center, and it goes much more slowly as it's outside. So it orbits very slowly outside, but it orbits very quickly when it's down in the middle. When the radius is small, the velocity goes up. And the opposite is also true. When the radius gets big, the velocity goes down. So planets that are orbiting very closely, if they have a small radius, they will have a rapid velocity. So Mercury is very close to the sun. It has a high orbital velocity. And something like Saturn is very far out, and its radius is big, and so its orbital velocity is much slower, like that. And this was one of Kepler's laws. Kepler's second law basically said, essentially what's in this boxed equation, is that things that are closer to the sun will orbit much faster, and things that are farther out will orbit much slower. So that's one conclusion we can get from this. Another thing that I want to point out as a result of this, this type of equation is I want to say Kepler had a third law. And his third law was basically this: the cube of the radius divided by the period squared, this should always equal a constant. And he said that this is true for every single planet. So if you took the radius of the planet and squared it and you divided it by the time it took to go around the sun, which is its period, and squared that, it would always be a constant. So that's true for every single planet, which is an interesting thing. How could he get that? Well, I'm going to show you how you get that from this boxed equation here. This is one description of velocity. So let me basically copy this guy and take it to the next page. And so once we get this description of velocity, I can also have a second description of velocity that's based on a sort of a simpler type of description. So if this is the sun right here, and now I'm going around it in a circular path, I can say the time it takes me to go around is the period. So that's t. So orbiting all the way, let's say from here, all the way around back to that same location, that's the period. And the distance that I go, if this is the radius of that orbit, the distance I go is one circumference. So the distance is 2 pi times r. That's the circumference of a circle. So velocity is given by some sort of distance divided by time. So for example, when you say that you travel 50 miles per hour, that's your velocity. It's 50 miles, that's a distance, divided by a time, which is an hour. 50 miles per hour. Velocity is just distance divided by time. So if I do that in this circular description, then velocity, v, equals the distance around the circle, which is just the circumference, divided by the time it takes, which is just the period. So now if I have these two equations, this one for velocity and this one for velocity, I can just set them equal to each other. So let's do that. Square root of g, mass of sun, divided by r equals 2 pi r divided by the period. Now I'm going to try to get to this relationship up here where I put r cubed over the period squared. So to do that, from this thing that I have here, I'm going to square both sides. So I get rid of the square root. And then here I square every term. 2 squared is 4. Pi squared is pi squared. R squared is r squared. And then I've got to square the period, like that. So I've got this, and what I can do now is manipulate this by multiplying both sides by r here and here. The r's will cancel, and I get g, mass of sun, equals 4 pi squared r cubed divided by the period squared. So you can see it's already beginning to look like r cubed t squared over t squared. And now I divide both sides by 4 pi squared. So I get g, mass of sun, divided by 4 pi squared equals r cubed over the period squared. This is Kepler's third law, what he called the law of harmonies. And so this says for any planet whatsoever, I can have this relationship between r cubed and t squared. It'll always be constant because the things over here, g is a constant. As I said before, I'd mentioned it, 6.67 times 10 to the minus 11th newtons meters squared, kilograms squared. So this constant is a universal constant. It is the attraction. It gives us the attraction between the sun and the earth, but it also gives us the attraction between two pebbles. It's very, very weak. These two things will be attracted. It's very weak because the power here is 10 to the minus 11th. It's super small. And you don't typically see a lot of gravitational force unless you have a large amount of mass, like the mass of the sun and the mass of the earth. But if I have this law of harmonies that's given right here, then I can say, for example, put in the radius of, let's say, Neptune and cube it, and say the radius of Earth and cube it. And if I know the period of Earth, which is 1 year, and square it, then I can find out, just by algebra, what the period of Neptune is going to be. And on one of your homework problems, you actually have this. So the goal is basically to figure out what this is, but you're given this, this, and this. So this is very powerful. And it also, by the way, allows you to calculate the mass of the sun. So the mass of the sun can be known if you know the radial orbit, the radius of the orbit, the period, and you know these other constants, including g, and as we talked in class, you can measure g. So then you're able to calculate these things. This is an extremely powerful insight that Isaac Newton had, because once this was all put together, then you could basically determine where the orbits of the planets would be. You could determine the masses of the sun and the earth and other planets from this type of thing. It opened a large change in our understanding of ourselves, which was seen as, in some ways, the high point of the Enlightenment, this period in the 17th century when we came to understand science, the scientific revolution, and all the things that it brought us, eventually leading to things like technology and the Industrial Revolution. But it all started with a better understanding of the universe and our ability to realize that our minds were powerful and could find these deep regularities in the universe. Okay, hopefully this was helpful. I told you how gravity is involved with circular motion, how it's related to the velocity and distance relationship, how it's related to Kepler's third law.